what I'd like to do is give you guys a little bit of background on titrations, and then maybe a little bit of an example of how we might do one. And you'll be able to use this to do the last sort of dry lab, unfortunately, that we have to do. Unfortunately, not that that you guys have to do it, unfortunately. Unfortunately, that we have to do it as a dry lab. It's such a great lab with great equipment and all that, and I'll try and sort of walk you through kind of how that whole thing works. So um, that's the main idea behind this recording here, to make sure you guys are ready to handle that dry lab that should be coming out here in the next day or so. Okay, let me get this out of the way and we'll talk about it. So the term I keep using is titration. So let's talk about what it is. A titration, you guys, is using a solution, an aqueous solution, whose concentration we know, in order to determine the concentration of an unknown solution. So if I have this solution, and we'll be using a very specific set of solutions here in our lab in order to do this, but you can do it with a lot of different kind of solutions. So if I have a solution and I'm trying to figure out for whatever reason what its concentration is, I don't know, then I can do what's called titrate it with another solution whose concentration I know probably because I made it, and excuse me, I know that guy's concentration, and so I can go ahead and figure out the concentration of a guy I don't know. Now, you guys have experienced this a whole bunch of times in your life, probably, even though you didn't know it was a titration. So, for instance, a couple of examples that you may have some experience with. If you've ever given a sample of your blood for a doctor in their lab in order to analyze your blood for things like electrolytes or iron content or fat content, cholesterol, any of those kind of things, or if you've ever had blood work done before, then that's a titration, right? What they're reporting back, if you ever look closely, I'm sure you never have before, but next time maybe you will. If you ever look closely at the output from your blood work, the report, right, that you get back, then it tends to report most of those things in a concentration, right? You recognize it as a concentration because it has an amount, it's a ratio that has an amount of the specific ion or whatever that we're looking at divided by the volume. So it's an amount per volume of your blood, which is a concentration. And so mostly what we're trying to do is understand and manage the concentration of these things in your blood, which, by the way, is an aqueous solution. If you've ever given urine for a urine sample, same basic idea, is that they're looking for certain things in certain concentrations in your urine. So they want to know the concentration of this particular thing, so they're titrating your urine. The same is true for breathalyzer tests. So if you get stopped by a police officer late on a Saturday night and they ask you to take this breathalyzer test, then they're trying to figure out the concentration of the alcohol in your blood, and so they're titrating it. So this is a really common type of thing. Now, most of this is done in really small amounts nowadays. We're going to do it on a macro scale, or we would have done it on a macro scale. And we're going to use a set of equipment that's what I would consider to be, the standard equipment you'd find in any chemistry lab in the country for doing, macro titrations. And that would look like this right here. Let me make this bigger so we can see the whole thing. So this is the equipment that we would have used. Right, so we would have used these things called burettes. These guys are about meter long, and we would have used 2 of them, and you would have the solution in one of them that you knew the concentration of, and the solution in the other one that you didn't know the concentration of. And then what we'd be doing is mixing them. You can see down here, do I have a color? I bet I don't. Let me give myself a color here. Um, so let's make you big again. Where'd you go? There you are. So this is the solution down here. This is where we're doing the titration down here. And so what we're doing is we're at this station here, we're adding a amount of solution. Let's call this solution A and call this solution B over here. And we're adding some A and we're adding some B. And we're kind of going back and forth between A and B until we get the results in the container down here, in the reaction vessel down here, that we like. Now, if we take a little bit closer look at these burettes, you can see they're kind of graduated and they have these little valves on them, so you can turn the valve on and off to allow some of the liquid that's in A and in B to fall down into the reaction vessel. But let's take a little bit closer look at those guys, and we'll come back to this here in just a second. So if we look closer at it, they look kind of like graduated cylinders, except they appear to be upside down. Remember, a graduated cylinder would have at the top, let's say it's a 50 milliliter graduated cylinder, it would have 50 milliliters here. It would have like 25 here, right? It would have like one, right here. So as you go down in a graduated cylinder, the volume markings get smaller. But notice as I'm going down in my burette here, notice I got 20, 21, 22. On this guy over here, 34, 35. So as I go down, I'm getting bigger. Okay, I'm sorry. I'm in the burette. I'm getting bigger. In a graduated cylinder, I get smaller. So the first time kids look at these burettes, they think they're upside down. They're like, what's up with that? How come it's getting bigger as I go down? So you can see if I'm measuring the volume, let's look at the one over here on the left, that the volume that I'm measuring right here is bigger than 34 and smaller than 35. It's somewhere in between those two guys. This guy over here, it's bigger than 20 and smaller than 21. So this volume in here is 20 point something milliliters, right? This volume over here is 34 point something milliliters is the way you read it. Now, I would spend a lot more time explaining this if we were actually using this equipment, but what I'm explaining here is that you have to have your eye right positioned right at eye level of where um, um, the liquid is within the burette, because if your eye was up here somewhere, right? So here's my eye up here, and I'm reading like this. Then I get a much poorer description of what the volume actually is. So you would be asked to keep your eye right there at what's called the meniscus. You get a good view of the meniscus over here on this picture over here as well. The reason you have a meniscus is because the water will not form a level in the glass burettes. The water's actually grabbing onto the sides of the burette. And so you have to read a burette the correct way. You have to read it from the bottom of the meniscus. As you can see what's happening right here, you have to read this across here. You cannot read it here, right? This is not the right spot to read it. Where we read it is at the bottom of this meniscus. So looking at this guy over here, we're trying to read somewhere around there at the bottom of that meniscus. So just taking a quick look at it, I would say that that's reading somewhere around 21.24, maybe 21.24. So the volume in this burette right here now is about 20.24 milliliters approximately, reading from the bottom of that meniscus there. Okay. Um, Unfortunately, as I said, you won't have to do that in class. But what we have to be able to do is read the volume in the burette accurately, and so that's what I'm kind of showing you guys here. Jumping back over to this other slide over here, what burettes actually measure is volume of a liquid. And in this particular case, what they measure is the volume of an aqueous solution. So if we wanted a very accurate measurement of volume, we would use a burette in order to do that. So keep that in mind as we start talking through how the process here actually works. So burettes measure volume. Okay, so we will be doing a what's known as a volumetric titration. So we are going to be keeping track of volume in order to figure out the concentration of an unknown solution. Okay, let me make myself a little bit of room here. So let me clear that off and bring this guy back around so that I can start writing about some of the chemistry here. All right, so here's the titration that we're going to do. What we're going to do is we're going to try and figure out the concentration of this guy. Okay, so we want to know what is this guy's concentration. Remember, square brackets mean concentration. And so in order to do that, according to our first slide over here, when we're doing a titration, we need to use a solution whose concentration we know in order to figure out the concentration of an unknown solution. So the unknown solution we're going to try and figure out is the HCl. And the known solution we're going to use, it's the sodium hydroxide. Okay, that'll be the known one in this lab that we're going to do. Normally, what I would have you guys do is make that solution so that you know for a fact that you know its concentration because you made it, instead of having to trust what somebody else made. That's why we did that original, or would have done that original lab, the making of a solution lab, so that you know how to do that. Okay, so here we are. What we're going to do then is we're going to use a solution of sodium hydroxide whose concentration is 0.5 molar is what we're going to do. Okay, so I made this solution for you. It's 0.5 molar. We're going to put that in this burette right here. And what we're going to do is we're going to put the HCl in this burette right here. And we're going to add those two guys together until we reach a very important point in a titration. That point is what's known as the equivalence point. Okay, the equivalence point. The equivalence point in the titration that we're going to do is when moles of HCl is exactly equal to moles of NaOH. Okay, so the equivalence point in general is the point where the moles of the aqueous solution whose concentration you know is exactly equal to the moles of the solution whose concentration you're trying to figure out. Okay, so that's what's known as the equivalence point. The equivalence point, like I said, in this lab that we're going to do is when moles of HCl and moles of NaOH are equal to each other. And that's a really important point because that makes our math really simple. And I'll come back up to this here in just a second, but just reminding ourselves, the molarity is equal to the number of moles of solute divided by the volume of the solution. And I'm gonna rearrange this equation and solve for number of moles of solute. So I'm going to multiply both sides by volume. And when I do that, right, volume cancels here. So the moles of solute is the molarity times the volume. So in this particular case up here, the moles of the HCl, which is the solute in this solution over here, is the molarity of the HCl times the volume of the HCl. And the moles of the NaOH, which is this solution over here, is the molarity of the NaOH times the volume of the NaOH. And those two things will be equal to each other at the equivalence point. That's the only time they'll be equal to each other. So the fun part of this lab is finding the equivalence point. And once you've found the equivalence point, then the calculations become really, really simple. So I already know the concentration of the NaOH, right? I told you that we made this solution. So the concentration of the NaOH is 0.5 molar. And then I've got a device that will allow me to keep track of the volume of the NaOH, and I have a device that will let me keep track of the volume of the HCl. So I'll know this guy and I'll know that guy. And so the only thing I don't know is the molarity of the HCl, which is what I'm going to find by doing this titration. So you can see the math becomes really easy. I just need to keep track of the volume of the NaOH and the volume of the HCl, and I already know the molarity of the NaOH, and so it becomes a plug and chug, as I'll show you guys here in just a second. Okay, so there's the basic chemistry behind this. Now, how would I go about doing this? Again, let me give myself a little bit of cleanliness here. So let's get rid of you. So how would I go about doing this? I'll show you some data collection here in just a second. So what I would do is I would fill these burettes up. They don't have to be all the way full, but I would get my HCl. By the way, this balances 1 to 1 to 1 to 1, right? Balances all ones. And so what I would do is I would fill this burette up here to about, I don't know, about right there. And then I'd fill, this is my HCl burette, and then I would fill in my sodium hydroxide burette, and I can't get them to the exact same height, so maybe I filled it to right there. And what's really important is that before I start titrating, that so I haven't put anything in my cup, in my reaction vessel down here. There's nothing in here in this reaction vessel, right, in this guy. And so what I'm going to do is I'm going to read those two volumes. So I'm going to read the volume of the HCl initially, and I'm going to write it down. And I'm going to read the volume of the NaOH initially, and I'm going to write it down. So before I started titrating, here's how much HCl I had in my burette. Here's how much NaOH I had in my burette. So I'm going to read those initially. And then what I'm going to do is I'm going to go ahead and take some of the HCl, and I'm just going to add it into my reaction vessel. So I'm going to let this run down to, say, right there. Okay, so I no longer have this much in there, but I wrote it down already, right? I wrote that number down. If I didn't, I'm in trouble. Okay, and then what I'm going to do is I'm going to bring my reaction vessel over underneath the sodium hydroxide, and I'm going to try and add sodium hydroxide to it until I get to exactly the equivalence point. And again, that's the fun part, you know, fun in air quotations here, and I'll explain why in just a second. And once I get it to the equivalence point, let's say it's down here, then I'm going to read the volume of the HCl finally, right, once I'm at the equivalence point, and I'm going to read the volume of the NaOH finally when it's at the equivalence point. And so those are the 4 pieces of data that I need, and I'll show you guys how to use them here in just a second. Before I do that, I want to go back to this fun part, right, about how I figure out when I'm at the equivalence point. So again, let me clean this off here just a little bit because I need this space. So got him cleaned off, and let's expand again. So here's the problem. The problem is that the HCl solution looks like water, and the NaOH solution looks like water, and the water looks like water, and then the sodium chloride solution looks like water. So I'm adding water to water and making water in something that looks like water. So I don't have any visible clues on when I'm at the equivalence point. So I need a visible clue that tells me when I've achieved this equilibrium point. And so in order to do that, we use, and usually I stick it up on top of the arrow here, we use this stuff called Fen. Okay, the reason I stick it on top of the arrow is because it's not part of the stoichiometry. It's just going to give us a visible clue as to what's going on. The Fen, which has this big, long, fancy name, phenolphthalein, right? I just call it Fen. Fen. right, in my class, is what's known as an acid-base indicator. And there's lots of acid-base indicators. Sort of the traditional one to use, certainly at the high school level, is Fen. Um, and the beauty of an acid-base indicator is it can sit in the reaction and not really participate, but it can give you a visible clue about when you have reached the equivalence point. Acid-base indicators, you guys, change colors when the solution moves from an acidic solution to a basic solution. So phenolphthalein has the following color profile. When the solution is acidic, phenolphthalein will be colorless. You might say clear, you might say transparent, right? You can't see it when the solution is acidic. When the solution becomes basic, then phenolphthalein becomes pink. And so it'll give us a visible clue when I've added in too much sodium hydroxide. Because when I've added in too much sodium hydroxide, then the reaction is going to become basic, right? Because I'll have extra sodium hydroxide in there. So what I want to do is I want to go ahead, if I back up just a little bit here, when I pour my HCl in here in the beginning, right? Remember, I was up here somewhere, and then I went ahead and poured some in, and now I'm down to here. Before I start adding any sodium hydroxide, right? Sodium hydroxide's still up here. Then what I'm going to do is I'm going to put a few drops of Fen in there. And when I do that, since the only thing I have in my container is HCl, the container will be colorless, right? Because HCl is an acid, and when Fen is in an acid, it will be colorless. And then what I'm going to do is I'm going to add sodium hydroxide, which is a base, right? This guy's an acid. This guy here is a base. If just stepping off topic for a second, if we had been in normal class, we would do one more unit after this called acids and bases, and so you would be much more familiar with the fact that sodium hydroxide is a base before we were doing this titration. Anyways, back on topic here. We're going to add sodium hydroxide until the solution turns pink. And once it turns pink, that tells me I added too much sodium hydroxide. So then what do I do after that? Well, I need the solution to not be basic, so I add more of the HCl. And I'm going to add more HCl till the solution turns colorless again. And then I know I'm really near the equivalence point because the solution just turned colorless again. And so now I'm going to add a little bit more sodium hydroxide, like one drop at a time, until the solution just becomes the slightest non-colorless pink. And at that point, I'm pretty sure that I'm right at the equivalence point. And so that's how I'll know what the equivalence point is. And so at that point, I might have moved the volumes down, to somewhere around here and here, like I was saying before. And so now that I've got this beautiful light pink, then I know I'm at the equivalence point, and now I'm going to go ahead and read my final HCl volume and my final NaOH volume. And then I'll have my data. Okay, so that's kind of how this thing's going to work. Now, what am I going to do with that data? Well, let's just jump ahead here just a little bit. Again, how to read this. We don't need to look at that again. So here's, the data that you would have gathered in your POGL group, in a POGL group I just made up. So the four of you would have gathered data. And so Joe, I'm totally making this data up. Let's say Joe's initial HCl was 40.62. The burettes read in milliliters. And Joe's final HCl was 31.22 milliliters. And Joe's initial NaOH, right, before they started adding any into here, was 39.61 milliliters. And Joe's final NaOH, after we reach the equivalence point, is, let's say, 30.1 0.16. Okay, so this is Joe's data, and so what we can do is we can use that to figure out the concentration of the HCl. Right? In order to do that, we would say the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And we know the molarity of the base, right? The molarity of the base of the NaOH is 0.5 molar. We know that again because we made it. So we just are going to plug that in right here, right? So we're going to say, well, the molarity of the base is 0.5. And what we're trying to find is the molarity of the acid. So in order to do that, we just need the volume of the acid and the volume of the base. And so here's a rhetorical question for you. Which of these volumes do we use down here? Which of these volumes do we use over here, right? So we need the volume of the base to go right here, but we have two volumes. And we need the volume of the acid to go right here. And again, we have two volumes. Which one do we use? And the answer is we don't use either of them. What we need to know is the volume that we need to stick right here is the volume of the HCl that we put in our reaction vessel. And so in order to find that, we are going to subtract the volume of the HCl finally from the volume of the HCl initially. That'll tell us how much we put in the reaction vessel. 40.62 minus 31.22. Okay, so we actually put in there 9.4 milliliters is how much acid we put in there. Yes, we can do this in milliliters. The volume of the base is the difference between these two guys. So 39.61 minus 30.16. So 9.45. So the volume over here is 9.45. This is in milliliters. And the only thing we don't know is the molarity of the acid. And so look how easy this math is. I'm just going to divide here by 9.4 milliliters. Divide here by 9.4 milliliters. That goes away. And so it looks to me like the molarity of my acid is going to be 0.5 times 9.45. And then we're going to divide that by 9.4. So the molarity of the acid in this case, 0.503 molarity HCl. And that's how easy it is, right? This is not a hard mathematical lab, you guys. I would tell you truthfully, it's hard to get that light pink that you're looking for. That's the hard part. But since we're not going to do that, I'm just going to give you what the final burette readings are here, and initial ones are. Then the lab's going to go by pretty quickly. Okay, so there you go. This is how we do titration calculations. What I'm probably going to do, just looking at this right now, is I'm probably going to give you some data for Joe, Mary, Billy, and Karen, and then have you guys analyze that data. I'll ask you a few questions about it in lab form, and then you guys will be able to do the calculations and knock this lab out pretty quickly. Okay, so there we go. I'm going to stop there. Well, actually, normally we would do another kind of titration called a mass titration, where instead of keeping track of volume, you'd be keeping track of mass. In this case, I don't think we're going to do that. And then lastly, I would give each individual an unknown. And so you guys would have to make your own solution to titrate it against, and then you'd have to titrate your own solution. And so it's the one lab in this class that you do all by yourself. And that's one thing I really loved about it, and that's why it took 3 days. So I'm going to try and get this down to something a little bit smaller than that. Okay, so I'm going to go ahead and stop there, and then I'll go ahead and prepare the lab, and I'll try and get that lab out there for you sometime tomorrow.